So one thing that's useful about this equation would be to find out the formula for the fundamental frequency, which would be the frequency of the first harmonic, or F1. We just have to put n equals 1 in there, and we get 1 over 2L times the square root of T over mu. And that means that the frequency of the nth harmonic will just be n times the fundamental frequency. So this is very useful. When you are doing the lab, you're going to have to find the fundamental frequency, but the fundamental frequency is not so easy to find. So sometimes it's easier to find maybe the third harmonic or the fourth harmonic, and then you can predict. Let's suppose, you know, you found out F4 was 2 hertz, and you know that that is 4 times the fundamental frequency. So then you know the fundamental frequency should be about 1/2 of a hertz. And if you can find then F4, if that's the frequency that you can identify when you're playing around with your frequency knob, you can use that to work backward and predict where the fundamental frequency will be, and it's easier to find it if you're looking in the right ballpark. If you start out with just low frequency, like 0.1 hertz, and go up to 0.2 hertz and 0.3 hertz, you can't really identify this so easily. So just keep that in mind. Maybe at the very end I'll demonstrate that again with the simulation. But generally, it's easier to find higher harmonics than it is to find the fundamental frequency. So you'll want to use that result. Okay, so let's try problems from the book and try to put it all together. So starting with college physics, problem 22.3. It says a horizontal cord 5 meters long, so L equals 5 meters right off the bat, has a mass of 1.45 grams. What must be the tension in the cord if the wavelength of a 120 hertz wave on it is to be 60 centimeters? So the wavelength is 60 centimeters, and it says it is a 120 hertz wave. So what is that talking about? That is the frequency. And just FYI, in case you are not aware, a 1 hertz is just 1 per second. It's like 1 over a second. Okay, so that's what a hertz is. And they asked us to find the tension. Okay, so we know that the velocity is frequency times wavelength, and the velocity is the square root of the tension over the linear mass density. So if I square both sides, I have tension over mu equals F squared lambda squared, and tension will be mu times F squared times lambda squared. Now, all I need to know is the value for mu and the value for lambda in the proper units. So they gave us centimeters, but we want to convert by multiplying the lambda by 1 meter over 100 centimeters. That is 0.6 meters. And mu, which is the mass over the length, is, we want to convert that 1.45 grams into kilograms. So that's 0.00145 kilograms over 0.6 meters. And that looks like 2.42 times 10 to the minus 3 kilograms per meter. So we're ready to go. The tension should be 2.4 times 10 to the minus 3 kilograms per meter times 120 per second. Then we square that. And then we're going to have lambda is 0. Hold on, I'm sorry, I put lambda in here instead of length. I just looked at the wrong number. We should have had the lambda is 5 meters. So, it's not writing. So this number was not the right number. So that is 0. Well, let's do it as 2.9 times 10 to the minus 4. Okay. So, and then my lambda is the 0.6 meters. So if we look at units here, we're going to get kilogram meters squared per second squared divided by meters. So we get kilogram per second squared, which is newtons. So that kind of confirms that we're doing the right thing with regard to the units. I get about 1.5 newtons. Then the problem goes on to say how large a mass must be hung from its end, say over a pulley, to give it this tension. So the idea is you have a tabletop and a pulley and a mass hanging, and then you know, this is a piece of string attached on the end of some kind of thing. Okay, the mass is what's creating the tension. So yeah, go ahead. Who was that who said so? Was that, maybe I just got an echo. Maybe I got an echo. Sorry, you guys might not have even heard that. So we have, there's tension here and there's tension there, but we know because of Newton's second law, since this mass really doesn't go anywhere, it just kind of hangs there, that the tension would have to be equal to the force of gravity. So if tension equals mg, then the mass we would need would be equal to the tension over g. So that's 1.5 over 9.8. And that would be 0.153 kilograms. Okay, any questions? Okay, let's take a look at another problem. Number 22.4. This one says a uniform flexible ball is 20 meters long and has a mass of 5 kilograms. It hangs vertically under its own weight and is vibrated perpendicularly from its end with a frequency of 7 hertz. So basically, we have a machine here that just kind of wiggles back and forth. And as it wiggles back and forth, a wave is going to propagate through this, this long cable. It says the frequency is 7 hertz. I'm going to reboot my screen real fast because it's I'm getting really, really long bad lag. Hold on a minute. I think I'm almost there. Okay, I think that's a little better. So it says the frequency is 7 hertz. Sorry about that. Find the speed of a transverse wave on the cable at its midpoint. Transverse means the kind of wave we're talking about, where we wiggle side to side. The other kind, which we really aren't going to talk about much, is longitudinal wave, and that's kind of what's happening when I'm talking to you, and the sound is getting compressed in the direction of motion, and it sort of travels. That would be like if I would take this string and move it up and down as opposed to side to side. Okay, so we want to know, it says at the midpoint. Find the speed of a transverse wave at the midpoint and what are the frequency and wavelength. So at the midpoint, there should be some kind of tension that is pulling down on the top and pulling up on the bottom half. And so that tension, it's kind of an action-reaction pair between the top half and the bottom half. The tension is equal to just half of the weight of the cable because it's basically supporting the bottom half of the cable. So then the velocity at that point would be square root of mg over 2 over mu. And that's the square root of mg over 2 times mass over length. And the mass can just cancel out. So that's going to be the square root of LG over 2. Just doing kind of the algebra first before I plug numbers in. And that is 20 times 9.8 over 2. So I'm getting about 9.9 meters per second for the velocity. Now we want to know the frequency and wavelength. Well, the frequency is determined by this thing that's wiggling it at the top. The waves just travel down, and you know what a 7 hertz frequency means is that thing at the top is wiggling 7 times per second. And that means that if you go any point in the rope, you're going to see 7 wiggles per second passing you. Even though the wavelengths of those may change, they may not be the same, but it's literally moving back and forth 7 times per second, and it's sort of forced to do that at all points in the string. So this is 7 hertz. Christian.
How did the length go from the denominator to the numerator in that fraction?
So the length is actually technically in the denominator of the denominator. So when I cross the m's out, it's like I have a 1 over L here. So if you have G over 2 times 1 over L, then you can multiply top and bottom by L, and the L cancels on the bottom and moves to the top.
Thank you.
Sure. Okay, so if we know the frequency and we know the velocity, we find the wavelength. Wavelength is just the velocity over the frequency. So that's 9.9 meters per second over 7 per second. You know, hertz is a 1 over second. So those 1 over seconds cancel, leaving me with just meters. And so the wavelength is going to be just 1.4 meters. Okay. Any questions? All right. Moving on to the next one, 22.9. So it says a string fastened at both ends resonates at 420 hertz and 490 hertz with no resonant frequencies in between. So we have a frequency, let's call it frequency X, which is 420 hertz. I don't know whether this is like the first harmonic, second harmonic, 10th harmonic. Then there's another frequency above this, which would mean it's X plus 1, that is 490 hertz. How do I know it's X plus 1? It's because they say there's nothing in between these two. So if this is the 10th frequency, this one would have to be the 11th. If this is the 5th frequency, this would have to be the 6th. Or else there would be something in between them. And we want to know what is the fundamental frequency. So we want to find F1. Well, all I know is that, you know, Fx plus 1, that would be n times the fundamental frequency. Sorry, not n. It would be x plus 1 using that formula, x plus 1. So whatever this is, whatever number that is, it would be that many times the fundamental frequency. And the x, maybe I should have called these n plus 1 and n, would be x times the fundamental frequency. So if I subtract these guys, I get x plus 1 minus fx. Again, think of this like the 11th minus the 10th would be equal to 11 times the fundamental frequency minus 10 times the fundamental frequency. When I subtract these, I just get fundamental frequency. So that means 490 minus 420 equals the, sorry, I'm writing this as F0 because I've used other books in the past that call this F0. I apologize. This is, your book calls it F1, and I need to stick with that. Fundamental frequency is F1. So when I subtract these, I get just 70 hertz. Now, let me make a comment about this problem before questions, because this thing I did with the fx and x plus 1 probably seems like something you won't think of, you know, if you haven't seen this before. But here's what's really happening. All of the frequencies have to be a multiple of the fundamental frequency. So you really look at 420 and 490 and say, you know, those need to both be multiples of some number. And if there's nothing in between them, then the difference between them will be the fundamental frequency, because the way the frequencies are going to work, it starts at 70, and then you have one harmonic at 70, and then you're going to have another at 140, and another at 210, and then 280, and so on, up to 420 and 490, and so on. So those are all multiples of 70. And that's always how it works. So you can kind of use that logic and intuition to solve this problem and just say, well, they're different by 70. They look like they're both multiples of 70. So that must be what the fundamental frequency is. It starts at 70, and then it sort of, you add 70 every time you want to get a new frequency. You just add 70 on top. And eventually you get up to 420, and then 490, and then 560, and so on. All right, any questions about this problem? Ziad.
So I'm just kind of confused how, when you say that f of x equals x times f of 1, and then you, like, how did you go to that next step, the third step?
This one right here?
Yeah.
I subtracted these two equations.
Oh, okay.
And then if it's not clear where this x times f1 comes from, it's really coming from right here, when we said the nth harmonic is n times the fundamental frequency. So if it's the x harmonic, it would be x times f1. If it's the 7th harmonic, f7 would be 7 times f1, and so on. Probably maybe x is not a good variable to use there because maybe it's a little confusing. Other questions? All right, then last one I wanted to do is 22.10. It says a violin string resonates at its fundamental frequency of 196 hertz. So F1 equals 196 hertz. Where along the string must you place your finger so its fundamental frequency becomes 440 hertz? So let's call this fundamental frequency 1, or F1A, and then we're going to make a new fundamental frequency by F1B by placing our finger, you know, somewhere along the soundboard. And so then that's going to be at I want to make an A 440 hertz on this string. And the question is, where do I place it? Okay, so we know that velocity equals frequency times wavelength. And that the velocity of the string is not going to change because we're not changing the matter of the string, we're not changing the tension of the string. So we could say F1A times lambda A must be equal to F1B times lambda B. So for the fundamental frequency, we know that the wavelength is 2 times L. So that would be F1A equal or times 2 times the length equals F1B times 2 times the length again. So this would be called length A and length B. Again, I'm going back to these pictures here where we saw that, you know, the length, the lambda for the fundamental frequency was 2L. Because of the picture that the fundamental frequency is only giving us half of the wave. The second half of the kind of ghost wave is off the picture. So now we can try to solve for LB. We can cancel these two. And we can solve for the length B in terms of length A. That's going to be F1A LA over F1B. And that is 196 LA over 440. And that is 0.445 times length A. So basically we have to cut the string a little bit more than in half by this certain ratio. If any of you are into music at all, it would be very interesting to see, you know, actually measure the violin and see how much is the pitch off if you're off by a millimeter. And I think you'll be amazed at how accurate violin players can be, considering how precisely they have to get these lengths. That's probably why they all use a lot of vibrato when they're playing, because that kind of distorts whether the note is just right or not. Okay, any questions? Anyone in here play violin? I used to play a little badly, so I don't do that anymore. All right, so that's it for today. Tomorrow is, I mean, I don't want to disappoint you, but tomorrow's our last lecture. And we'll be going over the same stuff, more problems, but we're going to look at what happens when we have, instead of a string, like a bar that's clamped like either a pipe, like an organ pipe, or a bar like on a xylophone or something along those lines. So there's a little bit different physics because the ends are not fixed on a pipe. So we're going to see how that changes things and then do a little bit more of the same kind of stuff. So if you have questions, as always, stick around. Otherwise, I will see you next time.